Yeah, I was gonna say that. Thank you.
Okay, moving on. And then I'll show you this other graph that shows you the voltage and current ratings of the available switches in the market. So you can see that for the lower power applications, we have MOSFETs. And then as the power goes higher, and just notice that, for example, for MOSFETs, the current limit is 1,000 amps. The voltage limit is 1,000 volts, but you don't get 1,000 volt MOSFET with a 1,000 amp capability. If you're looking at the higher range of the voltage, the current will be lower. The current might be like in the 100 or 120 amp range, right? Or if you're looking at the higher amp range, then the voltage is lower. The voltage might be like a I don't know, low voltage, less than 100, for example, in this case. So it's a compromise. I think the highest that it can go is around about 10K, 10 kilovolt ampere. And then we have basically IGBTs. So this graph shows the IGBT. So you have IGBTs at a higher power rating, and then when you go into the really high power ratings, you don't find that many transistors. You only find thyristors. So these are all type of thyristors that are available at the higher power side, right? So in the higher power, so when you go into megawatts, for example, then you only have thyristors in the market. And this other graph that I showed you shows you the power rating or the power capacity versus operation frequency. Remember that, as I mentioned, the analogy that I gave you was when you go into the high power ranges, switching on and off the device would be like opening and closing a hydro dam versus closing and opening of a hose, right? So if you have a hose at hand, you can create some kind of a switch that could switch it 10,000 times a second. But when you're dealing with thousands of amps, like in this case, for example, like 6,000 amps, then you should not expect to be able to switch 6,000 amps 10,000 times a second. You might be able to switch it 100 times a second, but no more than that. So that's why with these higher power ratings, you can see that again, we only have thyristors available. So these are only thyristors, GTO, TRIAC, and thyristor. These are thyristor switches. So at higher power ranges, we have these available, but the thing is their switching capability is limited. So the best or the highest frequency that you can get is 1K. That means that you can only switch these things maybe 1,000 times a second, but no more than that, which is still incredible. But if you're looking for something that you could switch where the switching frequency is much higher than that, so in the 10K, 100K or 1 mega, for example, in places that you want high quality audio, then you can't use, then you gotta basically use things like MOSFETs. So MOSFETs are the only switches that give you a really high switching capability. GTOs and thyristors are the only switches that give you a really high power rating. Okay, but the disadvantage is that then you don't get the switching frequency to be as high. Does anybody remember what was the reason for having to want high switching frequency? What was the reason that we wanted the switching frequency to be high?
Because high frequency filters are cheap.
I make it into a bonus question, so 1% bonus. Why would we want the switching frequency to be high? Yes, Karen.
Is it because there's less harmonics when you
what is the reason?
Is it because there's less harmonics when there's a high switching frequency and lower power capacity?
Sorry, I think my my speaker was off. Can you say that again?
Is it because it has a higher switching frequency? Sorry, the higher switching frequency means that you can use that there are less harmonics, so then you don't need as many filters. And
very good. Yes. So what I mentioned in our last lecture was that one thing that I wanted to remember is that switching frequency determines the harmonics. So the higher the switching frequency, the higher will be the frequency of your harmonics. And if your harmonics are at a higher frequency, it's easier and cheaper to filter them than if they're close to your actual frequency. So for example, if you have a waveform that looks like this, a sine wave that has a hash on it, high frequency hash, that's really easy to filter. But if you have a sine wave that looks like this, you know, like a pulse, this is not as cheap and easy to filter as the other one, because this is made up of sine waves that are close in frequency and amplitude to your original waveform. So ideally in power electronics, we want the switching frequency to be as high as possible so that we could push the harmonics into the high frequency ranges so that we could filter them easily. So you get your 1% bonus, Karen. Okay, now for switch selection. So there are so many different power electronic devices available. I mean, and they so much research is happening on these as well. I mean, for example, you can see that even in this graph, this was published in 2014, and then the dashed lines shows where the research was happening. So it shows the ratings of, for example, GTOs that are about to come. So they were working on GTOs that you could switch them at higher frequency, for example. Or they were working on transistor modules that could give you a higher power. Right now, transistors, they are, I mean, their power capability is still less than a meg. You see that? But the good thing is that you could basically switch them up to 10K. So you could get something that was around about 1 meg and switch it about 1K. But less than a megavolt ampere means that their application is really limited. So for example, you can't apply them to electric trains or high voltage DC lines, especially in Canada where we have great distances between our between our hydro dams and our cities. High voltage DC is something that is used much more than the rest of the world in Canada, or the majority of countries. So in most countries, they still use AC systems. It's only places that have countries that have countries that have a lot of land where the power source is much further away from the load center that requires HVDC. Did someone have a question? So so Pamela says, Mackenzie also replied correctly to the bonus question. Yes, so for bonus questions, I need you to raise your hand, if that's okay. And then Yeah, so if you don't mind, then I'm asking a bonus question so that I see who's first. Please raise your hand, then answer. And that way you get your bonus. I think Mackenzie also got a 0.5% bonus last time, so I think that should be enough to keep him happy for the time being, I guess. Okay. Now, so how do we select switches? Well, I mean, there's so many different type of switches, and so many of them look similar, sometimes sound similar, and in many cases have only a slight differences in properties. So they work the same, they have similar characteristics, but one of them might have, like, for example, better conduction resistance or something like that. How do we select what's best for our application? Well, usually you need a bit of experience. There are some general rules. The first rule is you got to see what kind of a source you have. So if you have a circuit where the source is DC, so for example, if you have a battery, it's better to start with transistors. Why transistors? Because they're cheaper and they can handle higher frequency. So if you're not looking at power ranges in the 100 Ks or megavolt ampere, if you're looking at electronics, it's best to use a switch that could give you those higher switching frequencies, so you could basically get away with using a cheaper filter, for example, right? So if you have a DC source, start with the transistor and see if a MOSFET, which has a high switching frequency, can do the job. So check the voltage and current rating and the switching frequency rating. See if a MOSFET can do the job. If not, IGBTs usually can give you are designed for higher power ratings. So see if an IGBT can meet your requirement. And if you couldn't basically do the job with a transistor, then you can look into thyristors. So thyristors are like GTOs or IGCTs. So we start with transistors. That means that either BJTs or FETs, because these give us the higher frequencies, but the power is not as high. If they couldn't do the job, then we move on to thyristors. So thyristors like GTOs, gate turn-off thyristors, or insulated gate. I don't know what the C stands for. Insulated gates, something thyristor. These give you lower frequencies but higher power ratings. And usually you don't want to use diodes for places that need switching control. So diodes are switches that you can't control, right? They turn on whenever the anode is at a higher voltage than the cathode terminal. So for DC input sources, so if we have a battery at hand, the switch that we want to basically select would be ideal if you could use a MOSFET, if not IGBT, and in the extreme cases, then we go to thyristors. Can anybody think of a place where the source might be DC? Where do we have a circuit that has a DC source, for example? Yes, Imran.
Is it in phones because the converter converts AC to DC and then the source is DC?
I missed the first part. Is it what you said?
In phones, because the converter converts AC to DC.
Yeah. So
yeah,
any place where you have a battery, right? in all places where you have a battery, you have a DC source. Another place would be solar. Solar panels, their output is DC. So you always need a converter that could convert DC to AC, and the switches in those converters will have a DC source. So that's where, for example, you could have MOSFETs as an option. You could look at MOSFETs as an option. So that's what I mean by DC input sources. Now, if the source is AC, then yes, Simran.
I was confused here. So if it is a DC source, I was confused that how does the wave have frequency, because DC is just a straight line.
How does it have frequency?
Yeah,
So the frequency. Yeah. So the frequency that you're talking about is the switching frequency, not the source frequency.
Oh, right? Okay, makes sense.
So how fast you can switch this on and off.
All right, thank you.
Now, if the source is AC, then we only have a few options. So, for example, triacs, you got to check to see if a triac meets the voltage and current rating. And a triac is like a back-to-back thyristor. So it's like a back-to-back diode that it can control when it turns off and when it turns on. An example of where you use a triac is in dimmers. A dimmer is what you use to basically dim the lights, for example. And in a dimmer, you have a triac that basically changes the average of the AC voltage, right? So you can basically determine whether you want to turn on here and turn off here, or like how much of the AC signal gets passed on. I mean, when you select different portions, then the RMS and the average changes. You create a lot of harmonics by doing this. So, for example, a waveform that looks like this will have a lot of harmonics. That's why all dimmers, if you ask a senior technician, for example, whether it's a good idea to have a dimmer in your house or not, they're going to say no, because you might see that your laptop burns after a while, or you might see the fridge not working properly. The reason for that was because old dimmers, they would introduce a lot of harmonics, and the harmonics could damage electronics in your house. But nowadays, I mean, they have a bit of filtering, and then they have other stuff with them that takes care of the harmonics. But the basically working principle of a triac is that it can control when the thyristor turns on and when it turns off. So you can basically change the RMS, or the average value of the AC waveform. And if you could change the RMS value, that means that you're changing the voltage. So you could basically change the voltage of the AC voltage, if you like. Just like a transformer, but the transformer gives you a nice AC signal. A triac gives you a distorted AC signal, but it's small enough to fit in a wall switch compared to a transformer, right? And it's much cheaper. So check to see if a triac meets the voltage and current requirement. If not, then check to see if a thyristor works. So yes, Pamela.
So is there no like straight answer? It would always be like circuit or system specific, and you have to test different things, or are there things that are like already standardized and you know what you use for everything?
again, it all depends. It's all based on experience, right? And with electronics, things are changing and improving on a yearly basis. So you have to be up to date, and you have to know what's available and what are the properties of each switch. And the
And
other thing is that,
okay.
and the other thing is that a lot of these things, I mean, you don't want to invent the wheel from scratch all the time, right? A lot of the time you got to see what's available in the market, because these come as pre-assembled packages. So you got to see what are the off-the-shelf devices available, rather than having to design these things from scratch.
And is there always one that is like the right answer, or sometimes, or you're like kind of like sacrificing one thing for the other and seeing which one has the least amount of
The
losses and
latter.
stuff like that?
So there is no super device yet, right? So the right one is that ideal switch or the super device, but none of these switches are ideal. So they all have some advantages and some disadvantages to them, and that's why we are looking at each one to see. I mean, we will be looking at each one to see what are the advantages and disadvantages of each one.
Okay, thank you.
Yeah. So if the triac and thyristor were not good options, then the other alternative that you have is to rectify the AC, make it into a DC. Remember that you can, with power electronics, you can do this at high efficiency. So you might lose 1 or 2%, or less than 3% anyway, of your power, but then you have a DC signal, and so the DC signal opens up a lot of other options for you. So now you can start looking at, for example, power MOSFETs, IGBTs, etc. So that's the other alternative that you have, right? But in selecting switches, you always have to. I mean, the main three things is, what is the source? What is the type of? Is it DC or AC? And then what is the power rating? And then what is the switching frequency requirement? Once you determine these, you can basically, you're halfway into selecting your switch, or you're 60 or 70% of the way there, right? The next thing that you have to check is to see what is the switching requirement. So what is the control requirement of your switch? So for example, do you want a switch that you only need to control when it turns on, or do you need to control when it turns off as well? Do you want the is the power, is the for example, voltage, does the voltage need to be unipolar, or does it need to be bipolar? Will the current be unidirectional or bidirectional? So will you have an application where the power is going back and forth, or is the power just going one way? So is your load a car's wheel? So for example, in a car, sometimes you're going up a hill, and so the power is going from your battery to the wheel. And sometimes you're going down a hill. So when you're coming down a hill, you want the energy to go back into the battery, right? So these also basically determine the type of switch that you need. And I think these two are mistaken, are typos. So these two should be here. Because MOSFETs and CoolMOSes, they don't have bidirectional current. If you remember all of the characteristics that we looked at for MOSFETs or for FETs, they were in the first quadrant. So the I, VDS, they were all in the first quadrant. We didn't have anything in this quadrant, in the third quadrant, right? Where the current is negative, for example, or the fourth quadrant. We didn't have anything like that. So the characteristics of all feds that we looked at, they were in the first quadrant. So I think these two are incorrect. So yes, Imran.
Could you please explain the meaning of unipolar voltage and bipolar voltage?
So unipolar voltage and bipolar voltage means a diode. Let's take a diode. It only turns on when you have positive, negative like that, right? It does not turn on if it's the other way around. But a triac, you could turn it on either way because you have two of them back to back, right? So in an application where you have a battery that looks like this, this is an example of a unipolar. So you have always the positive on this side, right? But if you have a battery that is AC, then you might have a negative on this side. So that determines whether the switch can work in a unipolar situation or a bipolar situation. Does it answer you?
Yeah, and so does that mean if something is something operates on unipolar voltage, it will have unidirectional current?
No, it doesn't necessarily have unidirectional current.
Okay. But why? Because the voltage will be just in one direction, so why will the current go in the other direction then?
Remember, we have 4 quadrants, right? So if this is voltage current, let's say current voltage, we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. And we can have, I mean, these devices could have characteristics in any 4 of these quadrants. So here, for example, in Q4, you have a positive voltage and a negative current. You get what I mean?
All right. Yeah, makes sense.
So that means that sometimes in some, the characteristic of these devices, I mean, we won't have, so you got to be careful because like these 2 quadrants are for generators. So if you enter quadrant 2 and 4, that means that your switch has now become a source. So none of these switches will work if you assume this polarity convention. So this polarity convention where the current is entering the positive side like a load. If you ever enter quadrant 2 or 4, that means now you have a source. And none of these are sources. These are all passive devices. But some of these may be able to go into the 3rd quadrant. So Q1 and Q3 are for loads, Q2 and Q4 are for sources. I don't think we can ever go into Q2 and Q4 because then that means that the switch becomes a source, and none of these are generators, none of these are sources of energy, they're loads. But some of these devices are capable of going into the 3rd quadrant. So for example, a Zener diode, you know that it can go into the Zener region, right? This is the 3rd quadrant. You can operate it here as well. But the majority of them, their characteristics are in the 1st quadrant.
Okay, makes sense now. Thank you.
Okay, so Pamela, did you have a question?
not anymore. Thank you.
Okay. So the two switches that I want you to look at are thyristors. Like, let's look at their properties. So if a conventional thyristor SCR, which is like a diode that you can control when it turns on, it only requires a pulse for it to turn on. So you just need to give this a pulse and it turns on. So you can control when it's turning on, but you can't control when it turns off. It only turns off when the voltage across it becomes negative. So you can tell it to turn on here, but it will turn off at this point, right? So you will end up with this kind of a shape. If you give it a sine wave as the input, right? And the other thing is that it can't handle bipolar voltages, so it always needs this to be positive, this side to be negative. Sorry, it can't handle unipolar voltage. So it's not a unipolar voltage. It's a is it the same one? Bipolar. So I don't know what it means by this, but I'm thinking it probably just means that you can have SCRs that are symmetrical. That means that you can have a diode that works in the Zener region. Unidirectional current, so the current only goes one way, and that's it. And the other one that I want you to look at is this one. I think this bipolar voltage means AC. So this is for AC applications. This is for DC applications. So you can use thyristors in AC as well. So that's the AC-DC source that we were talking about. I think it's just a poor choice of wording, but that's basically what this means. Now, for transistors, the other thing for transistors, what I want you to notice is that, for example, for a BJT, the way you turn on a BJT transistor is you apply a voltage or a current, if you like, to its base, right? As long as this current is applied to the base, the switch turns on. So the gate needs a continuous signal. You can't pulse it. But the good thing about it is that it can control when it turns on and when it turns off, right? And it can work with DC sources, and the current only goes one way. So the current goes from collector to emitter. Does someone have a question? Does that mean that you can use Zener diodes with AC sources too? Yeah, you can use Zener diodes with AC sources, but just remember that if you have a symmetrical AC and you're applying it to a Zener diode, you got to make sure that like the Zener only cuts the voltage on one side. It's not bidirectional like this. It only cuts it when you have a reverse voltage. So that means that it only cuts the voltage. If I apply a voltage here, a sinusoidal voltage, and let's say the peak is 10 and my Zener voltage is 5, it only cuts the voltage on the negative side. gonna have the reverse polarity, right? So the voltage becomes like that. You get it flat here. You don't get the rest of it. Okay. Now, so the other requirement, the main requirement, in addition to the voltage, current, and frequency rating, is, as I said, the control requirement. So you gotta basically know what are the control requirements for your switch to be able to do a good selection. So, for example, the thyristors, as I mentioned, as long as you have, it's like a diode that you can control. So here the input to it is a positive DC. The moment you pulse the gate, the output will, the switch will close, and so the output becomes Vs. But after that, no matter what kind of a pulse you apply to the gate, it has no effect on the output. So, for example, if you were using a thyristor for a DC-DC converter, it wouldn't work because you can't turn off the thyristor. So if you want something that you can also turn off, then you have to use either a GTO, MCT, or SIF, basically. These are all in the same category, right? And have a similar working principle, characteristic. So with a GTO, for example, if you give it a negative pulse, it turns off. And the control requirement is you only need a pulsing signal. So the controller should only pulse the switch. But if you use, for example, a transistor switch, then the pulse, the signal, the control signal needs to be continuous. That means that you can control when the switch turns on and when it turns off, but then the control signal also needs to be maintained. You can't pulse it. That means that you need that means that your control system will require more power. It'll consume more power because it needs to maintain the signal rather than just the pulse, right? So if you're using this switch for a tiny electronic pen, if you like, that has a small battery in it, this wouldn't be the wrong choice because it can deplete the battery really fast. You need something that only creates a pulse, and that's it. So that the control system doesn't consume that much power. Okay. And the same thing with MOSFETs and IGBT. So these are in the same category, right? These are transistors. These are thyristors. So as I said, the other thing that you have to check is the control requirement. And so once you've made certain that the voltage, current, and frequency ratings are met, then you also need to look at the control requirement and make sure that the switch that you're selecting works in that sense as well. Now, these were basically just an overview of the switches and the available power electronic switches, but you use these switches in circuits. So what are these circuits? There are 6 main categories of power electronic circuits. Rectifiers, direct rectifiers, that we call them uncontrolled rectifiers. We looked at these in the circuits course. Then we have controlled rectifiers that are sometimes called thyristor rectifiers. That means that for example, with direct rectifiers, you apply it you apply an AC signal to it, you get a rectified voltage. If you pass this through a capacitor and a Zener diode, you get a DC voltage. The average value of this DC voltage depends on your input. So if you apply this to, for example, the part coming out of the wall, you get, for example, let's say you get 24 volts. This 24 volts is constant. It does not change unless you change the input. But if you use a thyristor rectifier, then you can basically control the average value of your output. So you can basically change the output to change from 0 to 24 rather than just be a constant 24. DC-DC converters, sometimes we call them choppers. So that was the example that I gave you last time. So for example, if you have a 24 volt DC battery, how do you create 12? You can't do a voltage. I mean, you can do a voltage division with two similar resistors, but then you have to. I mean, your efficiency will be quite poor. I mean, even if you could call it an efficiency, sometimes you have to sometimes you have to basically give this voltage divider circuit 10 times what you require, what your circuit requires, which does not make sense. So you can't bring down the voltage using a voltage divider. Instead, we need a better solution that these DC-DC converters give us. And we have converters that can either chop down the voltage, so you can basically get, for example, 12 or 8 or 4 from a 24, and sometimes they boost the voltage. So you give it a 24 and they give you 48, 60, etc. We call them buck and boost converters, DC-DC converters. And then inverters. So inverters are circuits that you give them an AC input. Sorry, you give them a DC input, like a battery, and they give you an AC output. So DC-AC converters are called inverters. And then we have AC-AC converters. So these are something that we call AC voltage control. The triac that I told you is an example of an AC converter. So you give it, for example, a 120 volt AC input, and then that converter can give you 24 AC or 60 AC or something like that. It's like a transformer, but instead of giving you a nice AC, it gives you like a chopped up version of an AC that you need to filter. But the good thing about it is that it's much smaller, lighter, and cheaper. And sometimes you can use, and then we have other type of power electronic circuits that are simply just switches. So a switch that we can electronically control. So for example, if you have a substation that you want to make it smart, I mean, you've heard the term smart cities and smart grids and all that. Smart is another word for making it automatic. So how do you close this switch remotely, or how do you turn this area? How do you, if you have a neighborhood, how do you connect, for example, Siri to Burnaby automatically through a control center, and then connect it to Vancouver? Or disconnect them. You know, it's like, how do you connect these and disconnect these? So if you had switches that you could electronically control, then you could make this town into a smart grid. So these are at high power levels. At lower power levels, we can have like a UPS that I'm going to explain in the other slides. So we can use switches as, we can use power electronic devices as simple switches. Okay, so that's the other type of circuits that we are talking about. So for example, a DC motor. So if I use four switches, I can control the direction of a DC motor. You know that a DC motor changes direction based on the polarity that you give it. So for example, if I use sorry, this shouldn't be here. So these will be, yeah, here. So for example, if I close this switch and this switch, I get positive here and then negative here. Negative will be switched from, yeah, I think I forgot how to draw this, but I'll show you the circuit later on. So you can basically control the polarity of the motor using four switches. And these are basically the symbols that we use for these converters. So we have AC-DC, DC-DC, DC-AC, and AC-AC, okay, as a block diagram. Now, are we out of time? Seems we're out of time, huh? 12:30 already. Do you guys, do you have a class after this? Do you mind if you stay like 5 minutes over? You go 5 minutes over to 12:30? Actually, you know what? I'll just leave this part for Monday because there is like 4 or 6 different circuits, and I don't want to rush through these. So let's wrap it up for today. I think you guys are, the class for you guys is on Tuesday, right? So we won't, the long holiday won't affect you guys, affect this class. So we can finish this on Tuesday next week, the first half, and then the second half we'll start the next chapter. No, you don't have a lab. I think our first lab is probably either going to be on the 3rd or the 4th week. I got to basically work. I'm working with my TA to see when we could have that lab ready, but very likely that it's going to be the 4th week that we have our first lab. Mikhail, yes. For the DC-DC converter, would that need an inductor to boost the voltage? So we'll get to that. DC-DC converters are similar to the voltage multiplier circuit that we had. Remember the voltage voltage multiplier circuit, like the one that you could that could multiply the voltage by 2, 3, etc. So for the boost one, it's similar to that. It's a diode and a capacitor. And for the buck, it's just a switch that switches on and off. So we won't have anything magnetic in this one, in this class, but we have a lot of the circuits that we will be looking at are circuits that supply an inductive load. So the problem with inductive load is that if you have a switch and then your load is inductive, let's say the switch was just a diode. So if I had a diode here, and I had an AC voltage. Once the diode goes into conduction, it does not turn off until the current through it becomes zero. So that's something that we did not look at before. For diodes, we thought the moment the voltage across it becomes negative, it stops, but that's only true if we have a resistive load. If we have a slight inductance in the circuit, the diode keeps on conducting even in the negative voltage until the current through it becomes zero. Okay, so if I draw the current, they have a 90 degrees lag. So usually you have a resistor here as well. So it's not exactly 90 degrees, it might be like 50 to 40, 50 degrees. So if I draw the current, the voltage the diode keeps on conducting until the current across it, the current going through it is zero. Okay, so you end up with this kind of a circuit, or this kind of a voltage waveform, and that happens for all sorts of switches, and that's a bad thing, because in many cases we can that could cause short circuits, and so we'll be looking at how, like, circuits that would force the current to zero, and we'll analyze circuits not just with resistive loads, but also with inductive loads. So you have to basically look at the notes from the course 230 from circuits on RL and RC circuits, because there's going to be a lot of that here as well. Any other questions? Okay, if you don't have any other questions, then I think we can do the quiz. Actually, do you want to do the quiz, or let's just leave that for next week as well? But we have a quiz at the end of this lecture that we'll do on Tuesday. So please read the slides, come prepared. We're going to finish this lecture and then start the diode rectifiers next week. And enjoy your long weekend. I think we're going to have one day of sunshine, and the rest of it is going to be rainy. So enjoy the sunshine. Bye.